relativistic correction, and this we will do using perturbation theory. Okay, what we know from non-relativistic quantum mechanics, or that is true for even classical mechanics, that the kinetic energy of the electron is given by p square by twice m. Okay, but when we talk about relativistic formula, then in the case of relativistic formula, we have E square is equal to P square C square plus M square C4. This M naught is the rest mass of the electron, or in general of the particle. And then the total energy is also equal to, in all the cases where potential energy does not play any role, is the sum of kinetic energy plus the rest mass energy. I am representing kinetic energy by T. Okay? And then this E, since we have represented it as kinetic energy plus rest mass energy, this E, according to Einstein, is basically mc square and that is equal to P plus m naught c square. And what is this m? M is m naught by square root 1 minus v square by c square times c square. This is equal to T plus m naught c square. Therefore, when we talk about relativistic particles, then we have E square is equal to P square C square plus m naught square C4, such that E is a square root of this quantity and m naught is the rest mass of the particle. The total energy is sum of the kinetic energy plus rest mass energy. What is this total energy? This is mc square, and that is equal to m naught c square by square root 1 minus v square by c square. Is it all right? And we are going to talk about the correction to this part, because in our formalism we have considered p square by twice m. We have to consider how much would be this correction. Okay, now for that, let me start with p square c square plus m naught squared c4, that is equal to E square. Since in relativity P is mv, but this m is actually m naught by square root 1 minus v square by c square, and then we have v. Therefore, when I am talking about P square, this will be m naught square v square by 1 minus v square c square from here, and then you have a c square plus m naught square c4. And when you will take this is m naught square v square c square, you can write this as m naught square v square c4 upon c square minus v square plus m naught square c4, and this in turn will give you m naught square v square c4 plus m naught square c to the power 6 minus m naught square v square c to the power 4 upon c square minus v square. Therefore, this will cancel out, and what you will be left with is m naught square c4 by 1 minus v square by c square. I've just brought 1 c square to the denominator, and I'm writing it as 1 minus v square by c square. Therefore, your E square in relativistic formalism is m naught square c4 by 1 minus v square by c square. And if you notice from this expression, which is equal to m naught c square upon square root 1 minus v square by c square is t plus m naught c square. This implies that if we square both the sides, this quantity is nothing but t plus m naught c square whole square. Therefore, E square, you can write it as t plus m naught c square whole square. Okay? And what is there? E square? E square for all of us is p square c square plus m naught square c4. Therefore, you can simply write t plus m naught c square is square root, just compare this part and this part, t plus m naught c square is equal to square root p square c square plus m naught square c4. Okay? And I am going to use this expression to consider first order correction to the kinetic energy. Okay? Now I am changing the slides, and what I am going to do, I am going to bring this m naught c square to the right hand side, and in this expression I will take m naught square c4 common, and then when I will take m naught square c4 common, when I will bring it to the outside the square root, we will get m naught c square. Therefore, let me just write it as my t is p square c square plus m naught square c4 minus m naught c square. And this is what I am telling you, that I am going to take m naught square c4 common. We will have this as 1 plus p upon m naught c whole square, because m naught c square we have taken common, and therefore this is will give you 1 plus p square c square plus m naught square c4. 1 c square will survive, and when you will take square, you will have this term minus m naught c square. And we can take this m naught c square outside, and this is 1 plus P upon M naught C whole square to the power half minus M naught C. Now we are talking about correction to the kinetic energy. That means still we are in the region of non-relativistic limit, where we are considering the first order correction to the energy, and that means we are still considering that my P is smaller than M naught C. If we do that, then I can expand this, and when I will expand this, this will be M naught C square 1 plus, remember 1 plus x to the power n is 1 plus nx plus nn minus 1 upon factorial 2 x square plus dot dot dot. Therefore, this will be 1 plus half p by m naught c whole square minus half minus 1 upon factorial 2. That means this will be minus 1 by 8 p square p upon m naught c to the power whole 4 plus dot dot dot. And since I am taken m naught c square common, therefore from the last term we have minus 1. Okay, we have expanded this, ignored the higher order term, and this term, since we have taken m naught c square common, we have this as minus 1. Therefore, this is going to cancel with this, and what you are going to get is the following. See, this is p square by m naught square c square. When I will bring this m naught c square inside, what I am going to get is p square by twice m naught, and then minus p4 by 8 m cube c square plus higher order terms. Therefore, what you realize that if we are going to take the correction to the kinetic energy, then we have this original result. And how much is the correction? Correction is this much amount. Okay. Therefore, this would constitute my interaction Hamiltonian part. This is already there in my pure Hamiltonian, for which we know the solution. Okay, for hydrogen atom. This is the term which we are considering the relativistic effect, and we are taking the first order correction to the energy. Okay, therefore, this I will call it as the lowest order correction. And in our general notation, this is HI, this is equal to minus p to the power 4, 8 m naught cube c square. Okay, this is the relativistic correction, and using perturbation theory, we have to get the result at how much is this perturbation is going to change our original result. But at the same time, I had told you on the last term that at the alpha 4 order, alpha square is the 0th order, where we have e to the power 4, and then in the next order we have alpha to the power 4, and this we will see that this also turns out to be really alpha proportional to alpha to the power 4. But there is another factor or correction that is also of the order of alpha to the power 4, and that is known as spin orbit correction. Therefore, these two corrections then get added up to give you the total first order correction to the energy. Therefore, there is first order correction from the relativistic effect, and then the first order correction due to spin orbit effect. First, we are trying to obtain the first order correction due to the relativistic effect. And that means I am going to use this expression. I am changing the slide. Therefore, correction to the energy, we are talking about first order correction, En1. This is equal to, from perturbation theory formalism, HRI psi. And then we can write this psi n. HRI is nothing but P4 by 8m cube C square psi. Then we can take this minus 1 by 8m cube C square outside. This will be minus 1 by 8 m cube C square psi n p to the power 4 psi. Okay? And p to the power 4, we can write it as p square times p square, and p square is a Hermitian quantity. Therefore, in my next step, I can write it as 8m cube c square p square psi n p square psi. Therefore, what we have done, we have written p4 as p square times p square. And then we go back to the Schrodinger equation for the unperturbed state. What is the Schrodinger equation? This is p square by twice m. Actually, everywhere I should write not, but I am just writing p square by twice m plus v psi is equal to E psi. This is the time independent Schrodinger equation, such that what is p square psi from here? This is nothing but twice m E minus v psi. Twice m E minus v psi. Now I'm going to put it here. This will give me twice m here and twice m here. That will be 4m square. That I can take it out, the 4m square. Therefore, this I will write it as En1 is equal to minus 1 by twice m c square, and then bracket, we have E minus v on the right hand side and E minus v on the on the left hand side as well as the right hand side, but these are Hermitian quantities. Therefore, I can write it as expectation value E minus v whole square. And that means this will be E square minus twice EV plus V square. Therefore, what will be this? Minus 1 by twice MC square E square, because this E square we can take out and we will have this part minus twice E psi V psi plus psi V square. And this is a properly normalized wave. Our unperturbed wave functions are always properly normalized. This will be 1, and then this we will write it as expectation value of V, and this will be the expectation value of V square. Therefore, this expression is minus 1 by twice MC square E square minus twice E V plus V square. Now we know that what is our V? This is the Coulomb interaction energy. This is minus E square by 4 pi epsilon naught R. Therefore, when we will put it, E square and 4 pi epsilon naught R, they have nothing to do with the expectation value. We can take them out, okay, and then we will write it as, actually this is the first order correction to the energy. I should write it in the proper way because we are writing in the, for the nth state, this is En square plus twice En. Minus sign has become positive because we have a minus over here. Twice En, E square by 4 pi epsilon naught, expectation value of 1 by R, plus E square by 4 pi epsilon naught whole square, expectation value of 1 by R. Okay, this is the first order correction to the energy when we have taken the next to leading order term in the expansion. Now that means we are supposed to get the expectation value of 1 upon R and 1 upon R square in the case of hydrogen atom problem. And what I had told you, that you should try to obtain expectation value of 1 by R, that you will get is as 1 upon n square A, where A is the Bohr radius, which is half angstrom, and then 1 over R square, 1 over L plus half n cube A square, where n is your principal quantum number and A is the Bohr radius, and depending upon the value of n, your L will vary. Okay, if you are able to obtain this expression, then that is fine. Otherwise, I will do it and will send you a PDF file, because it is not possible to do in the class. There are too many topics, and this is a topic which was supposed to be done in M.Sc. B.Sc final year, but still I will, if you are unable to do, I will do it in the and send it a PDF file. Therefore, the first order correction to the energy, the relativistic effect, this is minus 1 upon twice. M is here M naught, mind it. Just I am writing is twice MC square plus twice En, E square by 4 pi epsilon naught, 1 by N square A, plus E square by 4 pi epsilon naught whole square, 1 over L plus half N cube A. And if you can recall, what is this A Bohr radius, half angstrom? This was actually in the Bohr model 4 pi epsilon naught h cross square by me square. Okay, therefore if you put everything in terms of epsilon naught and E square in the above expression, and you know what is the energy of the nth state in the hydrogen atom, if you can recall, this value is, I have written it also in the very first turn when I had started discussing hydrogen atom problem, Me by twice h cross square n square E square by 4 pi epsilon naught whole square. This is the expression where you, when you get for the unperturbed Hamiltonian, that means with P square by twice m mu as the kinetic energy term, where mu is the reduced mass of the system, and then minus E square by 4 pi epsilon naught as the Coulomb interaction energy. Therefore, when you will put this in the above expression, the expression that you are going to get is the first order correction to the energy is En square by twice m c square 4n L plus half minus 3. This will be the first order correction to the energy using which you have obtained using perturbation theory. But what I had told you also that actually in literature there exists the full description of relativistic theory of spin half particles, which we call by the name Dirac theory for the spin half particles, where the Hamiltonian is written as C alpha dot P plus beta MC square, but that is in your next semester. That is why here we are using perturbation theory, and we are writing the expression which is coming when you are considering only the first term of that relativistic expression. But still what you are assuming that your m naught c is much larger than the momentum of the particle. That means still you are in the almost in the non-relativistic limit. Okay, because in general it can be comparable, it can be more, the p can be more than m naught c when you will take, so for example you have 100 MeV electron and you have rest mass of the electron is only 0.5 MeV. Therefore 100 MeV of kinetic energy of the electron and 0.5 MeV of the rest mass, then you cannot apply this formalism. You can apply this formalism only when the kinetic energy of the electrons, they can be they are small, and with respect to the masses of the particles, here the mass of the electron. Okay, therefore mass of electron is 0.5 MeV. The energy in a hydrogen atom is much smaller than that. Therefore you are able to apply this relativistic correction. Otherwise if it is more than 0.5 MeV, then for sure you need Dirac theory for relativistic electrons, and that gives you the full formalism to calculate the energy of the electron in hydrogen atom or in any other process. But mind it, the most important point is all the relativistic formalism in the non-relativistic limit will give you the same result. Okay, therefore it is not that when you consider relativity and you find that your non-relativistic approximations are still valid, are still giving you the results which are which are acceptable because they agree with the experiments. When that means when we apply non-relativistic limit to the relativistic theories, then we will get a formalism which will match with this, which will agree with the present formalism. That is why first we try to understand by extending to one term, and then if we want to be more robust, then we consider relativistic theory for the electrons, and that is the Dirac theory. Now I am disconnecting it, I am going to reconnect it, and I will start the discussion on spin orbit coupling. Okay. Now we are going to discuss spin orbit coupling. Okay. Before we start this discussion, let me go to the 12th class physics book and recall the Ampere's law. When we say that we have a conductor through which a current I is flowing, and we want to calculate the magnetic field at distance r, perpendicular distance r from the loop, then what we do, we draw an sorry, very sorry, draw an ampere. This screen is so sensitive that instead of circle it is drawing every amperial loop. Okay, and the magnetic field and the element that we consider on this, they point in the same direction and they are tangent to this. Okay, then we obtain the magnetic field using Ampere's law, as B dot dl is mu naught times I, and since B and dl, they are pointing in the same direction, therefore we write it as B dl is equal to mu naught I, because at all the points on this circle the magnetic field would be, magnitude of the magnetic field would be the same, and then this is nothing but 2 pi r mu naught I, and finally this will be mu naught I upon twice pi r. This will be the magnetic field at point r. Okay, now if the electron is revolving around it and the mass of the electron is me and its velocity is v, then the angular momentum is equal to rmv. What is v? V is the circumference of the circle upon the time required to complete one revolution. Therefore, this L is Rm 2 pi r by t, or t is equal to twice pi m r square by L. Therefore, time period, you can write it as twice pi m r square by L, or magnetic field as, and magnetic field as mu naught I by twice pi r. This is from class 12. Okay, but we are students of M.Sc, and therefore we have to think differently. And what is that? When we say that in a hydrogen atom, electron revolves around the nucleus in a circular orbit with quantized angular momentum. Okay, this is true when we consider that we are sitting in the nucleus rest frame. Then the electron is revolving around the nucleus in a circular orbit with the angular momentum defined by ln is equal to nh cross. Okay, but if you are in the rest frame of the electron, okay, now in the rest frame of the electron, that means from the electron's point of view, the proton is circulating around it. Okay, and that means instead of a negative charge circulating around a positive charge, what is happening? A positive charge is circulating around a negative charge. Therefore, electron is here and positron is circulating around. Okay, and the distance would be the same, because whether you consider the nucleus sitting at rest or an electron revolving it like here, or you assume that electron is at rest and positron is revolving around it, that r would be the same. Now the important point is the orbiting positive charge, the orbiting positive charge, that means I'm talking about proton, would set up a magnetic field B in the rest frame of of electron. Okay, and this magnetic field will exert a torque on the spinning on the electron which is there at the center, because electron is a spin half particle. Therefore the electron will have its magnetic moment, and is this external magnetic field is going to apply a torque on the spinning electron. Okay, this magnetic field will exert a torque on the spinning electron and would try to align its magnetic moment say mu along the direction of the magnetic field, along the direction of the magnetic field. Therefore the Hamiltonian of this interaction would be given by the interaction between the magnetic moment of the electron and the external magnetic field which is coming up because of the proton. Therefore this is the magnetic moment of the electron or of the electron, and this is the magnetic field created by proton. Now the important point is that B which we derived in this case would remain the same, because now electron is moving around the proton is moving around the electron, and then this current B is equal to mu naught I by twice pi r. What is the current? Current is E by T, where this is the charge of the proton, and what is T is again the period of the proton to complete one revolution. Okay, therefore the important point is that now the magnetic field is mu naught I by twice pi r, and this I is E upon the time period, and E is the charge of the proton, and time period T is the time required to complete this full revolution. Now the important point is whether it is the electron which is revolving around the proton or the proton revolving around the electron, the required time period would be the same, otherwise the physical system won't exist. Okay, therefore the time period, whether we obtained it by as this or the time period which we are talking here as E upon T, they both would be the same. Okay, and the direction of this, therefore we have the positron which is moving like this, we have a distance r, and then what I am telling you, the dipole moment of the electron and the magnetic field, they are in the same direction. They are in the same direction. Okay, L and B, they are in the same direction. Therefore what I am going to do, I am going to put this value of mu naught I by 2 pi r, instead of I will write it as E upon T, and instead of T I will write this expression. Therefore what we will have is the following expression. B is equal to 1 by 4 pi epsilon naught E upon mc square r cube L, where I have used c square is equal to 1 by mu naught epsilon naught. That means instead of writing mu naught, we are writing it in terms of epsilon naught and c square. Therefore, we have the magnetic field as 1 by 4 pi epsilon naught E by mc square by r cube L. This will be the magnetic field that is important, and that we'll be talking about. Now, the important point is that the magnetic moment, dipole moment, which we talk about the electron magnetic moment turns out to be minus E by m times S. This is, you may treat it as the standard value, because this will be obtained when you will learn the Dirac relativistic theory of electron, that the magnetic moment of the electron is given by minus E by m S, where S is the spin of the electron, and purely this a factor of 2 arise here, which is because of the relativistic theory, and that is beyond the scope of the present discussion. But the important point that you have to learn is that mu is this expression and B is this expression, and then we have to obtain what will be HI, and HI is minus mu E dot B, and that would be minus and minus will become plus. This will be E square by 4 pi epsilon naught m square c square r cube L dot S, and this is nothing but the term which we should obtain when we are considering that the proton is revolving around the electron and the electron has got a dipole moment. Okay, but till now we have assumed that electron is revolving around the proton with a velocity v, but electron in itself always accelerates as it moves around the nucleus, and that is known by the name accelerating electrons, because this is not purely an inertial system. Therefore, when you want to do the kinematic correction to this factor, that is known by the name Thomas precession, which is purely a kinematic effect arising due to the fact that the electron accelerates as it moves or revolves around the nucleus. Okay, this is known by the name Thomas precession, and when you consider this precession into account, then instead of HI we have a factor of HI prime modified form, and we get a factor of half here, and that means a factor of half means this will become E square by 8 pi epsilon naught. Therefore, we'll have E square by 8 pi epsilon naught m square c square r cube L dot S. This is known as spin orbit interaction. Okay. Now, this part is not directly of our relevance, because what we need is the expectation value. Okay, what we need is psi unperturbed Hamiltonian, discorrection, perturbed Hamiltonian, psi n. Therefore, on Monday, I will try to evaluate this expectation value. Again, in this expectation value, as you can notice, we have all these as the constant terms. Therefore, what we are required to get the expectation value of L dot S, and we would be required to get the expectation value of 1 over R cube. We will try to obtain the expectation value of L dot S and expectation value of 1 over R cube to get the first order correction due to spin orbit interaction. Okay, let's stop. I will start from this point on Monday. Thank you.